So the goal in this section is to do and solve some optimization problems. What that's going to mean for us is we're going to have to look at the description of the problem and figure out several things. One of which, of course, is going to be the function that you use to optimize and try and find the best, the biggest, the maximum or the minimum that satisfies some conditions. So in this first one, what we're doing is we're cutting corners out of a little sheet of paper, folding this up into a nice box, and then calculating the volume. Now, depending on how much you cut off of the corners, that's going to change the volume of your box. So fold them all up like that, and then maybe tape them shut like the nice ladies did for me over here. And that's your box. You can calculate the volume, length times width times height. So these are the different values that we get. Of course, we can't just cut out just any old value for x. There's some constraints on our x, right? Why are there some constraints on x? Well, our original grid was 14 by 18. So when you start cutting out corners, if you cut out too much, you're not going to have anything left. For instance, right now we cut out 3 from each corner, so 14 minus 3 is going to, or 14 minus 6 is going to be 8. So there's 8 squares left here. So we can keep going. We can cut out another square and then another square. But pretty soon you're going to get to the middle, and you're going to be cutting out everything. So you won't have anything. And what that's saying is that there's kind of an interval over which you want to maximize your function. So the most that I could cut out and still leave myself some material to form a box would be 7. Now, does it make sense for me to cut out exactly 7? Or can I cut out as much as I want close to 7? Well, if I cut out exactly 7, then I'm not going to have anything left. So I'm going to put a parenthesis around that. And on the other hand, what's the least that I could cut out? Zero. Zero. Yeah, you have to cut out something. Now, can I put a bracket or parenthesis around the 0? Parenthesis, yes. Now, this is my interval. That's the values for which this function is going to make sense. Now, the function itself, that's going to be this part. We got to figure out a function for this. So let's go back to our little figure here. The original dimensions of this are going to be 14 by 18. So 14 that way and 18 this way. And x is how much we're going to cut out of each of these corners. It's a little x by x thing here. I need to find the volume formula for a box like this. So when I start out with something that's 14 wide and 18 tall, and I cut out this x by x, let's see if I can't figure out the volume. The volume is going to be the height. That height is going to turn out to be an x. So v of x is going to be an x. How much is left for the width? If I cut out x this way and x this way, how much is left for the width? Not 4x, but 2x. Because you're cutting out a length of this and a length of this, so you're cutting out 2x from the length. How about in the height here? How much is left in the height if I cut out, you know, x this way and x this way? How much is left for the height? 18 minus 2x. And that's your formula. So that's the one that we're going to try and optimize. Now, in this particular example, we want to try and find a formula, or so we want to try and find the point that maximizes this volume. So that's where the calculus part comes in. But are we okay with the setup? We started out with a nice picture of our graph, or a picture of our problem. So this is an x, this is 14 minus 2x, this is 18 minus 2x. And the volume of that turns out to be this polynomial function. Now, maybe we want to FOIL that all out, figure out what that is, because right now, if we're going to try and differentiate this and work with it, you'd have to use the product rule, and that would be kind of a pain. I think I'd rather just FOIL it out and use the, just differentiate it as a nice polynomial. So let's do that. I'm going to bust this over to another sheet of paper. So this is example A. So v of x is x times 14 minus 2x times 18 minus 2x again. Let's FOIL these two out first before we do anything else. So let's see, this is going to be x times 14 times 18 is going to be 252 minus 28x minus 36x plus 4x squared. Combine like terms, 252 minus 64x plus 4x squared. And finally, I'm going to distribute that and then reorder it at the same time. So it's going to be 4x cubed minus 64x squared plus 252x. So that's our function. So far we've gone through 3 steps. Draw a picture, we need our function, and we need to look at the interval over which this is defined. So remember, our domain for this problem, not the domain for this cubic function in general, but the domain for the problem is 0 to 7. So it's important to keep that in mind as we do this problem. We don't care about critical points outside of this because it doesn't make sense relative to the problem. The last part of this is the analysis. I need to find where this function has a maximum. How are we going to do that? Yeah, the derivative, which is pretty much our only trick at this point, but it's a good one, and it works here. So the derivative v prime of x is going to be 12x squared minus 128x plus 252. And great, I got the derivative. What am I going to do with the derivative here? Yeah, set it equal to 0. So let's set that equal to 0 and solve. Now there's a couple ways you can solve here. But if you had to solve, then one way is a quadratic formula. I don't think that these are going to turn out to be very nice, neat values for x. So maybe let's employ a little bit of technology here. So I'm going to plug in the first derivative, the first derivative into my graphing calculator, 12x squared minus 128x, oops, 128x plus 252. I want to know where this actually equals 0. So my thing is that I'm going to graph it, and I'm only going to bother graphing it in the window 0 to 7. Why 0 to 7? Yeah, that's our domain. That's where we're interested in working with this function. Sure, it's defined outside the domain, but that's okay. We're not interested in anything outside the domain because it doesn't really form a box relative to our problem. As far as the rest of this is concerned, I'm going to graph this from, say, 0 to, I don't know, let's take a look here. Let's go 300. and I'll scale it by 50. See what we get. Now those choices are informed, for me in this case, by this graph. And you know what, even if I got it wrong, I'm sure you know what? I am gonna need to see a little bit below the x-axis, so let me change this up just a little bit. We go y min, let's like y min maybe negative 100. We'll see. We can always go back and adjust this as needed. And that works pretty good. What we're interested in is finding this point where the graph crosses the x-axis. Does anyone remember how I could do that? Yeah, we're gonna go to the calc menu. So second calc, we wanna find the 0. So that's option 2. Now you need a left bound. So you got a cursor over, so you get to the left of wherever your root is. Press enter, then cursor back to the right. Press enter again, and then press enter one more time for reasons that I won't bother to explain. You should get about 2.605. So as root. Are we okay with finding that value of x? Now here's a good question for you. How do I know that this value of x represents a maximum point? Maybe I accidentally found a minimum point for this graph. That would be bad. So how can I guarantee myself that this is a maximum? Say again?
Plug it in.
Plug it in? Plug it in will tell me the value of y, 2.605. So f prime is 0 here. But let's take a look at the graph. What's the graph telling me to the left of 0? What's the function doing?
Slope's positive.
Yeah, the graph is above the x-axis, so it's positive, which means, as Ethan was telling us, that the function's increasing. To the right of 2.65, what happens to the graph? It's negative, so it's decreasing. Great. So it's decreasing. So if you go from increasing to a critical point to decreasing, what kind of a point does this have to be? Has to be a max. In this case, it's a local max, but relative to our function on the interval 0 to 7, it's really the absolute max. So this is great. This is the first derivative test. The first derivative test just says that if you've got a critical point and the sign of the derivative goes from positive to negative, past that critical point, then that has to be a maximum. If we went from negative to positive, then that point would have to be a minimum point of some sort. Another way to approach this, in terms of double checking that this is actually a maximum, would be to figure out the second derivative. So let's find the second derivative, v double prime of x. What's the second derivative going to be there? 24x minus 128. Now what does the second derivative tell us? Who remembers? Nick?
Concave up, concave down.
Concave up and concave down. So one of two things can happen depending on the value of your function, depending on the function and where you're looking at. But basically it's going to be concave up and concave down. So if you have a critical point, place where the derivative is 0, and then you calculate the second derivative, well, the second derivative is going to tell you what the shape of the graph is near that point. So if it's concave up, then this is going to have to be a local min, or an absolute min, depending on the problem. Local min, whereas here, this is going to be a local max. What has to be true in order for your graph to have a concave up shape? Matt?
Negative on both sides of the X point.
I was thinking in terms of the concavity. What's the value of the second derivative if you have a concave up shape? Is it positive or negative? Try again?
Positive.
There we go. Cool. All right. So if v double prime, or if f double prime of your critical point is greater than 0, then you've got a local minimum. If f double prime of some critical point is less than 0, then you've got a concave down shape through your critical point. You've got a local maximum. So let's see what happens for us here. If we do v double prime of 2.605 of 24 times 2.605 minus 128. Now I don't necessarily need the exact value. Even if this was a 3, that would be like 24 times 3 would be 72 minus 128. It's going to be negative. So this is going to be less than 0. If it's less than 0, then you've got a concave down shape. The concave down shape is saying, all right, well, this critical point has to be a maximum. So let me use this little triangle of dots. You seen that before? Triangle dots? Yeah. All right, so it means therefore. Therefore, 2.605 is a max by the second derivative test. I would like you to double check that your points are doing exactly what they're supposed to do on your exam. So are we okay with either one of the first derivative test or the second derivative test to test your points? Let's actually find the dimensions of this box. So we know that this is the 2.605, but you've got a length here and a height here. So L and then H. Let's figure out these dimensions. X is going to be 2.605. As far as the other two dimensions are concerned, there's something nice that your calculator does for you. Take a look at this value. It's kind of long and not too user friendly, but if you clear out of here, if you exit the graph, type X. What do you notice about X? It's got that value stored in it. So if I wanted to find, say, 14 minus 2x, I can do that. So 14 minus 2x is about 8.79. So 14 minus 2x is about 8.790. And then 18 minus 2x, bless you, 12.790. So those are the dimensions of your box. That's the one that maximizes the volume. Sweet, sweet. So there's 4 parts to these types of problems. And that's how I'm going to grade you on your exam. Picture, function, interval, and the last part is the analysis. So picture, function, interval, analysis. I allocate some points for each of these, and then I look through and give as much partial credit as possible. But try and get as many pieces of this puzzle as you can. Let me stop for a second. Yes?
Do we have to do both the first derivative test and the second derivative test?
Great question. No. All I did was I demonstrated what the second derivative test is and the first derivative test, and I'm showing you that they give you the same conclusion. But no, just pick your favorite. Whichever one is most convenient. Sometimes one is more convenient than the other. So if it's the second derivative test, go with that. A lot of times your second derivative might just be a number. in which case it's always positive or always negative, so it's always concave up or down, and then you'll either have it'll always be a minimum or maximum. So yeah, great question, thank you. Anything else? All right, let's keep going. Move on down to example B. And I've got links for all these things. So if we look at the link for the first one, where is it? No, that's not it. Where did that one go? All right, vertical distance, line of box. There you go. You can see here that the function, is nicely defined between negative infinity and infinity, but outside the interval 0 to 7, it really doesn't serve us much purpose. So that's why we maximize the function in that interval. So about 2.6 something. Yeah, it looks pretty good. Let's keep going. Our next one is going to ask us to minimize the vertical distance between two functions. So our two functions look like this. One of them is y equals x squared plus 1. The other one was x minus x squared. You might recognize that both of these are going to be parabolas. So kind of draw a little graph here. And let's open up the appropriate link. I don't want that one. Leave. Where is it? Leave. There we go. So the graph's going to look like this. Here's your function, x squared plus 1. It's going to be a parabola that faces up. And then g of x is x minus x squared, a parabola that faces down. And somewhere there's going to be a value of x that minimizes the distance between these two things. So, okay, not so bad. We just got to figure out where it is. But this is your picture. So let's start with that. Just kind of jot something down for ourselves. So we've got a nice parabola that faces up like that. So that's in red. And then I'll do another one in blue. That one's going to face down. But what we're trying to find is the value of x, at which point the distance between the top and the bottom function, this distance is a minimum. Now, depending on what value of x you choose, that distance is going to be bigger or smaller. We're going to find the one that minimizes that. But anyways, there's your picture. Now, when it comes to finding the function, as far as the function is concerned, let me remind you that we're working in Calc 1. And sometimes I joke or say or remind you that Calc 1 is calculus of one variable. When you get to Calc 3, then you can start working with 2 and 3 variables. But right now, we're just able to work with one variable. So we need to find a function of one variable. So that distance is going to be the distance between these that we want to minimize is going to be the top function minus the bottom function. Now, there's nothing wrong with starting it out in words and then working towards figuring out an actual function. Now this coordinates, we can call that, say, x1, y1. This coordinate, maybe we'll call it x2 and y2. But top minus bottom is going to be, just y2 minus y1. And that's not really a function of one variable yet. But what we can do and remind ourselves of is that y1 is this function. x squared plus 1. And y2 is the other function, x minus x squared. So, okay. y1 is going to be x squared plus 1 minus y2, which is going to be x minus x squared. If you distribute that negative sign and simplify things, what do you get?
2x squared minus x plus 1.
Perfect. 2x squared minus x plus 1. And that I'll call, say, d of x. That's our distance function. The distance between the top and bottom. Okay, so this is example B. Picture function interval. So our function d of x is 2x squared minus x plus 1. Interval. Are there any natural restrictions on x? Could I look for x to the left? Could I look for x to the right? Or is there some restriction in there? Nothing like the last one. Nothing like the last one where we got a place where the volume was 0 at x equals 0 or x equals 7. So, okay. So our interval is just going to be negative infinity to infinity. There's no restriction on x. And that's going to happen from time to time. That's okay. Now, do I expect to be stretching out towards negative infinity to find a minimum? No. If you actually looked at the graph and played around with this, you can see the value of the top minus bottom. And, you know, it gets pretty big if you move to the left. And it gets pretty big if you move to the right. So somewhere in between there is probably going to be your minimum. And, you know, it's going to be somewhere in and around here. And you can play with it and get pretty close. But let's use calculus to find the exact value. Picture function interval analysis. Let's work on the analysis part. Shreya, suggestions. What should I do here? I want to try and find the value of x that minimizes this function.
Take the derivative.
Yeah, take the derivative. So the derivative here, Julia, easy one for you, derivative.
4x minus 1.
4x minus 1, great. Let's set that equal to 0 and solve. That's going to be x equals 1/4. So, okay. Now, how do I assure myself that that's actually a minimum?
What's the second derivative?
Yeah, in this one, I would use a second derivative test. So, Joshua, what's the second derivative here?
Just 4.
Yeah. D double prime of x equals 4, which is always positive. So if the function's always positive, what's its shape then going to be? What kind of shape am I going to have for this graph? Yeah, it's going to be concave up, meaning my critical point here at x equal 1/4 has to be a minimum point by the second derivative test. So minimum point we put x equals 1/4 is a minimum point by the second derivative test. Beautiful. Let's cheat a little bit and make that equal to 0.25 exactly. And there you go. The distance, the vertical distance at that point is 0.875. Although you really weren't asked for that vertical distance, you were asked for the value of x that minimizes that vertical distance, and that would be this. X equal 1/4. Not bad, not bad. Mason?
On the exam, are we gonna have to show how that we can prove that that 1/4 is actually the?
I think it's a good idea. There's a lot of other points and value that goes towards grading this problem. But, you know, either this last step here of showing that your point is actually a minimum, it's either gonna be a point or two of credit or a point or two of extra credit. Either way, it's probably in your best interest to include that. But, you know, if you got down here to x = 1/4, my inner child's gonna be doing somersaults. I'll be really happy for you there. But, you know, you probably should go a little bit farther and make sure that that's actually a minimum. Anything else? Let's keep it rolling. Example C. Find the distance between a point 4.2 or 4, 2 and the sine curve so that that distance is a minimum. There's a little trick here, a couple little tricks that you're gonna have to pay attention to. So let's first of all look at the graph for this one. Station, no, where is it? I just don't have that one opened. Distance. Distance to function. There we go. So here's what's going on. There's your point 4, 2. And you want to find the point on the sine curve that minimizes the distance between the point 4, 2 and your sine curve. So you can play around with this a little bit, move it back and forth, and you can see the distance from this point to the curve, depending on where you're at on the curve. Now, it looks like the minimum distance is going to be somewhere around here. So closest I can get is probably around 0.416. So let's see if we can't figure out what coordinate points would be here at that point. So it looks like it's going to be about x is 2 something and y is just under a half. Let's actually find out. Let's go through all our steps. Now on the exam, I regret to tell you that you're not going to have these really cool graphs. Sorry. Not much I can do there. But we got them here, and take advantage of that. Example C. And I'm going to give you a wide variety of these types of problems so that hopefully you won't be so lost in the homework. So here's our point 4, 2. Here's our sine function, or at least a really cheap facsimile thereof. I want to find the point that minimizes this distance. So let's call that distance, say, x, or that point on the curve, x and y, since we don't know what it is. And there's our picture. Next, I need a function. Well, the function is going to have to be the one that, or at least start out as the one that calculates the distance between these 2 points. So you remember the function that calculates the distance between 2 points. What's that look like? Lath, you look like you got that.
The square root of x2 minus x1. Minus over y1.
Square root of x2 minus x1 plus y2 minus y1. Both of those get squared. All right. So I want to use this. And let's see. Well, we can plug in x and y and 4 and 2 and get the square root of x minus 4 squared plus y minus 2 squared. Okay, that's looking better. But how many variables does this function depend on right now? 2. And as a reminder, we need a function that depends just on one variable. Now there's a couple things I'm going to do here. First of all, let's figure out how to make this depend on just one variable. and I'm looking at this and realizing that, well, y equals the sine of x. Does that help me at all? Yeah. I can write this as x minus 4 squared plus sine of x minus 2 squared. Okay. And really, I could write this as d of x now, because this function depends just on one variable. And that's what I want. I want a function that just depends on one variable. So, okay. But we're going to do something kind of sneaky here. And I remember being a student, and this kind of really bothered me. But minimizing the distance is going to be the same as minimizing the square of the distance. So I'm going to square both sides. Katie, what's d squared going to represent then? Or what's d squared going to equal?
It should just be x minus 4 plus sin x minus 2.
Good. And the squares don't disappear. We're just going to get what's called the radicand when we square both sides of this. And it'd be kind of annoying because our derivative notation often involves a d. Kind of annoying to use a d for this. So let me just call this s of x. That's the distance between this point and this one squared. And minimizing this is going to be the same as minimizing the distance function. With the benefit that minimizing this, I don't have to work with the square root there. It's going to make the derivative a little bit easier to work with. Okay. Now what? What steps next? Somebody whispered it. Interval, thank you. So the interval. Is there any restriction on x? Does x have to be a certain place or could it be anywhere? I mean, it's unlikely to be anywhere, but can it be anywhere? Yeah, it can kind of be anywhere. There's no real restriction on x. Now I've got some restrictions here to create this Desmos thing, but not real restrictions. There's nothing that restricts your value of x from being any particular value. Now it's likely that it's going to be somewhere here. We'll actually have to find out. So our interval, once again, is negative infinity to infinity. Picture, function, interval, last step. Analysis. When all you got is a hammer, everything looks like a nail. And really, the only hammer we got right now is the derivative. We're going to use that. So take a moment and calculate the derivative. If you're watching this later, pause the video, calculate the derivative for yourself. Don't forget the chain rule. What do we got? Someone tell me what you got. S prime of x. Homology. What'd you get when we differentiate this part?
I got 2
Mm-hmm.
in brackets x minus 1 times 0 inside that's 1.
Good. So drew the outside times drew the side. Drew the inside's 1. Good. Plus.
2 sine x minus 2. Then cosine x.
Perfect. Now here's the fun part. Here's where Isaac Newton could come to the rescue. Seriously, literally, and in section 4.8. We need to set this derivative equal to 0 and solve. Now, solving this one would be kind of a real big pain. So Isaac Newton created a method, which has now come down to us as Newton's method, for solving where a function is equal to 0. And that's going to involve some calculus. For right now, let's just plug this into our calculator and use our calculator's capabilities to find where this is actually equal to 0. So let me clear out all this old stuff here. Enter in our function. We're just going to look at the derivative. I'm not going to plot the first, the function itself. 2 times x, try it again. 2 times x minus 4. You can distribute if you want. For some reason, I'm just keeping it in parentheses. Plus 2 times sine of x minus 2, parentheses cosine of x. Now, before you play around and hit the graph key, there's something that you should check. What is it? Does anyone know? The window, and one other really important thing. Calculus is done in radians. You absolutely got to make sure you're in radians. I don't know as though there's a reason in a Calc 1 class to ever switch over to degrees. Just keep it in radians. So there's our function. Now, as far as our window is concerned, I think we could probably get away with some of what we had from the last one. So, in looking at this graph, yeah, 0 to 7 should be pretty good. Now, I'm not sure what to expect on the y-axis. And if I'm not sure what to expect on the y-axis, one workaround is to hit zoom what? Zoom 0. There you go. Beautiful. Beautiful. So there's 3 places where the graph crosses the x-axis. This first one, somewhere between between 2 and 3, and then one just to the right of 5 and one just to the right of 6. We're trying to find a minimum point, right? So which one is it more likely to be? This first one here or the second one? Why can't it be the second one? What's happening with the function's derivative here? It's turning negative. So if it goes from positive to negative, what was happening with the function around this point? It was increasing and then starts decreasing. So this one can't be a minimum point. This one could be a minimum point. This one could be a minimum point. So let's find both of those. Let's see here. Second, calc 0. Left bound, and then a right bound. And then enter. So I got 1 point at 2.65. So x equals 2.65, 1, 1, etc. And I'm just kind of curious about the other point. Let's see, so the other point, let's see, second calc 0 again. This time I want to go all the way over to this one. Enter, enter, enter. And 6.128. So both of those are minimum points by the first derivative test. Or excuse me, wait a minute. Let's see, it was decreasing and then increasing. Yeah, that'd be a minimum point. So we're looking okay there. It's just which one's more of a minimum point. Well, I guess we'll plug them back into the function and find out that distance then, or at least the distance squared. Let me clear this and let's calculate, let's see, x minus 4 squared plus parentheses sine of x minus 2, and then square that. 9.17. Let's compare that to the other value of x, or the value of the function at that other value of x. So take 2.6511 and store it in x. And then I want to evaluate this same function at this new value of x. Rather than type this all in again, just cursor back up, press enter to bring that down, and bam. So the minimum point is certainly going to be at this latter one, 2.6511. Nice. 5. Okay. Comments or thoughts on that particular problem? I guess the one last thing I could add here would be the sine of that value. Sine of x. Yeah, about 0.471. So that's the coordinates of the point. Here's your x value, here's your y value, where you have that minimum. That's what it looked like from the graph. It's around there someplace. Anything or thoughts on minimizing the distance here?
Why does why do we use the distance formula in this one? We use just y minus
Or the previous one? In the previous one, we were just looking at a vertical distance. So there was no difference in the x coordinates. So the difference in the x coordinates would have been 0. And then you'd end up with the square root of something squared, and those kind of cancel. And if you're doing top to bottom, then it's just going to be exactly what we did. We subtracted as to get the vertical distance. That's all you had to do is get the vertical distance.
comparing like two graphs, the x value is always gonna be the same for them because one is.
If you're dealing with a vertical distance, and let me just kind of dial this around here a little bit. It doesn't like that one. But if this was straight up and down, there'd be no difference in the x coordinates. They'd be the same. So then the distance formula that I have here, that would be a 0. And then I have the square root of this squared, which is just going to be y2 minus y1, which is the top minus the bottom, exactly what we did.
Gotcha.
Appreciate the question. Let's take a break. I'll put this in 2 parts.